Okay, welcome to Chapter 9, Part 3. In this video, we're going to talk about the factors that affect SN1 and SN2 reactions. There are 5 factors, as you can see here. We're going to go over the attacking species and how the nucleophile affects the outcome of these reactions. Then we're going to talk about concentration and how that affects these reactions. We'll also cover leaving group and the substrate itself. Specifically, we're going to be looking at steric hindrance. And finally, the solvent. So before we get started, just do a quick review question. Give this a try on your own and see if you can remember which of the following is the best nucleophile. Okay, hopefully you got this correct. The best nucleophile would be E, hydroxide. Remember, nucleophile is going to be nucleus loving, so it's going to be electron rich. And this is going to be the most electron rich. BH3 is not going to have electrons. Boron only has 3 bonds, so it's going to have an empty orbital. H3O plus is positively charged, so not the best nucleophile. Water can be a nucleophile, as can this alkene here, D, but the better nucleophile is going to be the one with a negative charge. Okay, so let's move on to looking at nucleophiles. And you can see here that the better nucleophiles are always going to be the stronger base. So as I mentioned in the previous slide, hydroxide is going to be a better nucleophile than water. Correspondingly, methoxide is going to be a better nucleophile than methanol. So always the stronger base will be the better nucleophile. Okay. The exception is going to be when we start looking at size of bases, so you could potentially have a strong base that's bulky, and then it might not be a very good nucleophile, but we'll get into that later. So you can see here, stronger bases correspond to better nucleophiles, and this is mostly going to be the case. So let's look at how nucleophile strength is going to affect the rate of the SN2 reaction. This slide is showing you some nice nucleophiles over here, so you can see water is considered to be a not so good nucleophile. And as the nucleophilicity gets better, so you can see good nucleophiles over here, the rate of the reaction is going to increase. So something like cyanide is going to have a much faster reaction rate than something that is a worse nucleophile over here, like water. So if we're looking at these different types of reactions, you can see here that when you have a better nucleophile, you are going to have a better reaction. So if we're looking at the Hammond postulate and how this is going to correspond, right? In both of these situations, the transition state is closer in energy to the reactants, okay? And so that means that if we're going to look at the Hammond postulate, right, this would be what we call an early transition state because it's closer in energy to the reactants. Down here, we also have an early transition state, but it's not as close, right? Look at the energy barrier. We have a larger energy barrier, so that means the transition state is less similar to the starting materials than in this case, where the energy barrier is lower. And you can see that the products over here, they're actually going to have similar stabilities. So this top situation is going to be a little bit faster. Okay, the idea being that Br minus is more stable. So things that are more stable, right, or things that are weaker bases are not going to be as good nucleophiles. So Cl minus here is a little bit better nucleophile because it's less stable. And you can see that in this reaction coordinate diagram because there's less energy or less of an activation energy for this to react. Now let's talk about SN1 reactions. So here we can see nucleophile strength and SN1 reaction rates. And you can see here that we have a couple of good nucleophiles, and the rates of both of these reactions are going to be very similar though. If we were to go back and compare NCS minus with N3 minus of the SN2 reaction rates, right? You can see over here that they have different reaction rates. But for the SN1 reaction, the rates are similar, basically the same. And that's because if you remember with the SN1 reaction, we're just waiting for the leaving group to fall off. That's the slow step. Once the leaving group has fallen on, the nucleophile can come in. So it doesn't really matter what the nucleophile is. In the case of the SN1, the rate is going to be more dependent on the leaving group and not dependent on the nucleophile basically at all. So I mentioned before, the other factor that can affect nucleophiles is size. You can see over here that T-butoxide, which is a nice strong base, is bulkier in size, which makes it a worse nucleophile than something like ethoxide, which is less bulky. So if you have something that's large and bulky, it's not going to make a very good nucleophile because it's just too sterically hindered. It can still be a good base, but in this case, it's not going to be as nucleophilic. Okay, so that's all we have for nucleophiles. Let's now look at steric hindrance. So steric hindrance is going to play a significant role in SN2 reactions because all of this reaction is happening at once. You can see over here that we've got our T-butoxide trying to do an SN2 reaction, and it's just too bulky, right? And you can see down here that what it can do is it can do its acid-base chemistry. Okay, so the bulkier you get, the worse of a nucleophile you're going to have. So kind of looking back at this size factor is going to play a huge problem in the SN2 reaction. So if we just kind of summarize what we learned about nucleophiles, we learned that stronger nucleophiles are stronger bases. Weaker nucleophiles are going to be weaker bases. And we also know that strong nucleophiles are going to promote SN2 reactions. Weak nucleophiles favor SN1 because SN1 reactions do not depend on the nucleophile for the reaction. Okay, so why don't you give this clicker question a try and see what you can think here about these reactions. Now keep in mind that even though we haven't really gone over the E1 a lot in this chapter or at all in this chapter yet, we did go over the E1 previously. So just try to give this one a try. Okay, hopefully you got B, SN2 only, because basically what happens with the SN1 and the E1 is that they're just waiting for the nucleophile to fall off. So the attacking species is not going to affect the rate at all for either of those reactions. SN2 is going to be a second order reaction. It depends on both the nucleophile as well as the substrate. Okay, now let's take a look at our second factor, the leaving groups. Leaving groups are going to be better if they are weaker bases when they come off. So anything that is a bad leaving group is going to be a strong base. And you can see that over here on the left side. These are pretty strong bases, right? And over here, these are your good leaving groups. So in this diagram, we're looking at the rate of the leaving group in terms of the SN1 reaction. And you can see that it's highly dependent on the leaving group. So better leaving groups are going to have a much higher reaction rate. And these over here are going to be resonant stabilized leaving groups. So they're going to be very good leaving groups because they are weak bases. We've got other types of good leaving groups. They're going to be things like halogens, right? Weak bases. And then your bad leaving groups over here are your strong bases. So good leaving groups, of course, we know that they're stabilized by size, right? That's why I- is a good leaving group. We also know that electronegativity stabilizes them. That's why our halogens are good leaving groups. And of course, resonance can also stabilize our leaving groups. So let's briefly go back and talk about what reversible reactions mean in terms of kinetic versus thermodynamic control. So reversible reactions are typically going to be under thermodynamic control. And if you remember those thermodynamic control reactions, the products were very favored, right? We had a much lower the products were much lower in terms of the reaction. So if we were kind of to look at one of these, let's go back and pull that up really fast. So this is what I mean by lower. This is a thermodynamic control. we have favored, the final products are more stable, and you can see that we have a nice big delta G overall. So those reactions are technically, they can be reversible, right? But since they're so favored thermodynamically, it makes it really hard for them to go back over that hump. Irreversible reactions are typically going to be under kinetic control. These happen really fast, so we really want those reactions, since they happen so fast and since there's such a small energy barrier, they need to be irreversible, otherwise they're just going to go back and forth. So let's apply this to what we know about substitution reactions. So here's an example of an irreversible reaction, right? We have a pretty low activation energy here, right? But the reverse is very large, so it's hard for this reaction to go backwards. And you can see here a very strong base in a good leaving group. So this is irreversible, and it is a favored reaction. A reversible reaction is going to be something where the leaving group and the nucleophile maybe have the same, they're very similar. So I minus is not a great nucleophile, right? Br minus is a good leaving group, but so is I minus. So this reaction is potentially reversible, because you can kind of see here that even the products really aren't favored. So this can go back and forth. The activation energy both ways is going to kind of favor either side of the reaction. So this reaction is going to go back and forth. So what we really need in a reaction, if we want it to proceed, is to have a good leaving group and a good nucleophile. And we want our nucleophile that's coming in to be a better nucleophile than the leaving group that's falling off. So if we look at various leaving groups, right, these are going to be kind of what we consider to be our good leaving groups over here in red. Decent leaving groups are these ones in black. And then our poorer leaving groups are these blue ones over here. And these are all things that are starting to be strong bases. Remember, the weaker the base, the better the leaving group. And so if you were to think of this chart backwards, on this end, these are going to be better nucleophiles, and these are going to be worse nucleophiles. Okay, so next let's talk a little bit more about sterics. And in this case, before we were talking about the sterics of the base, and now we're going to look at the sterics of the substrate. And what you can see here for SN2 reactions is that these less hindered substrates, for example, methyl and primary, are going to have a much faster reaction rate than something that's more sterically hindered, like a secondary alkyl bromide or a tertiary alkyl bromide, which basically is so slow it really can't do SN2. If you look at the reaction coordinate diagram for these reactions, and you can see that here, this is an example of a methyl undergoing an SN2 reaction, and it has a relatively low activation energy. The more steric hindrance you add to the substrate, so over here you have a secondary alkyl bromide. This one has a much higher activation energy because it's more sterically hindered. And so if you think about it, a tertiary substrate would be even higher, and so it basically can't happen. So let's just do a really quick review quicker question. Give this one a try. Hopefully you remember. Okay, hopefully you remembered that the tertiary carbocation here is going to be the most stable. And this is going to help us when we're talking about SN1 reaction rates. Now with SN1 reactions, remember that the first step in the reaction is that leaving group falling off, right? So what you see is that tertiary substrates are actually going to be better for SN1 reaction rates, because once that leaving group falls off, you have a more stable carbocation. A primary substrate is going to give you a primary carbocation, which is very unfavored. So this is essentially not going to be able to do an SN1 reaction. And a methyl can't do it at all. A methyl carbocation is just not going to happen here. What about sp2 or sp hybridized carbons? So if you're looking at these and we're thinking about, okay, well, can a nucleophile attack these centers? The answer is no. You can't really have SN2 reactions on sp2 or sp hybridized carbons. So what you have is you have an electron-rich nucleophile trying to come in and kick out a leaving group, and there's just too much electrons in this double bond, or in this case the triple bond, and the electrons are going to repel the nucleophile. So you basically have something electron rich trying to come in and attack something that's electron rich, and this just isn't going to work. For a kind of, also you cannot have SN1 reactions of sp2 or sp hybridized carbons, but this is for a different reason. So with SN1 reactions, you're just resulting with an unstable carbocation. So if you have an sp2 or sp hybridized carbon, you cannot have SN1 or SN2 reactions. Some of these may be able to undergo other types of mechanisms that look like substitution, but there is no SN1 or SN2 on sp2 or sp hybridized carbons. Okay, so just to summarize our steric effects, if you have a secondary substrate, then you could potentially have an SN1 or an SN2 reaction. Tertiary substrates can effectively only undergo SN1 because they need that stable carbocation. And primary substrates effectively can only undergo SN2. So why don't you try a clicker question here and see if you can figure out what mechanism this reaction is going to undergo. Hopefully you got B. This is a primary alkyl bromide, and primary substrates can only undergo SN2. If it were secondary, it could potentially also undergo SN1. Okay, here's another review question. Why don't you give this one a try and see if you can identify the polar and protic solvent. Hopefully you correctly remembered that D, ethanol, is polar and protic. If we were to go through and classify these other solvents, A is going to be polar aprotic, B is just going to be nonpolar, and C and E are going to be polar aprotic. So why do we care about solvents? Well, solvent is going to affect SN2 reactions and potentially SN1 reactions. So in SN2 reactions, what you have is you have a very electron-rich nucleophile. So you actually don't want polar protic solvents. So polar protic solvents can potentially hydrogen bond with your nucleophile, and this can cause all sorts of problems. So one, they can actually potentially react, but two, they're going to kind of surround this nucleophile and prevent it from reacting. So you can see in this, reaction coordinate that protic solvents are going to significantly slow down the rate of these SN2 reactions. The activation energy is a lot higher. So what you want for these types of reactions is polar aprotic solvent. And this is kind of shown in the reaction rate. A polar protic solvent is going to give you a very slow reaction rate, like methanol, water. Polar aprotic solvents like DMSO, DMF, acetonitrile, and HMPA are going to give you great reaction rates. You don't have to, we don't usually use HMPA, that's not a common solvent, but I would say DMSO, and DMF, acetonitrile, those are ones that you should know and recognize as promoting SN2 reactions. So I did mention that your nucleophiles can potentially react with a solvent. So let's say you wanted to do this reaction here. This is an SN2 reaction. The nucleophile is attacking, and then the leaving group is falling off, all in the same step. So let's say you were trying to do this reaction, and you accidentally added water. Well, guess what? Your nucleophile here can react with water, can do acid-base chemistry with water, and that can result in hydroxide, which could then do an SN2 reaction with your bromide over here, your alkyl bromide. So you would actually end up with a lot of this side alcohol product and probably very little of the amine you were trying to make in this situation. For SN1 reactions, we actually want a polar protic solvent. Polar solvents, as you can see here, can stabilize those carbocation intermediates. Remember, your carbocation intermediates are very reactive, so any way we can stabilize these is going to be very helpful for increasing the rate of the reaction. So you can see here that this more polar solvent, right, is going to have a lower energy transition state, and that's going to be favored and help increase the rate of this reaction. Another thing that you'll notice with SN1 reactions is frequently the solvent is also the nucleophile. So for example, if we're going to use this alkyl bromide to make an alcohol, you would probably just use water as the solvent. And so there's so much solvent floating around, so much water, and it's also the nucleophile, that the presence of the increased amount is it's just going to come right in. So this is kind of the best way to run these SN1 reactions, is just to use a nucleophile that is also the solvent. Okay, so why don't you quickly give this clicker question a try and pause the video and see what you can come up with. So hopefully you were able to identify that SN2 reactions are going to be best if you have a good nucleophile and a polar aprotic solvent. Polar protic solvents are going to promote SN1, and also poorer nucleophiles are going to promote SN1 reactions. So this brings us to our SN1 and SN2 reaction summary. We talked first about the attacking species in the nucleophile. And remember that good nucleophiles are going to promote SN2 reactions. And good nucleophiles are going to be things that are strong bases and are small in size. SN1 reactions are unaffected by the nucleophile because the reaction rate, is going to depend on the leaving group only. In terms of concentration, SN1 reactions are going to increase with concentration. SN1 reactions are going to be unaffected by reaction concentration. And that's because SN2 reactions, right, are going to depend on two things, the nucleophile as well as the substrate. And the SN1, again, is unaffected by the nucleophile. So if you increase the amount of the nucleophile, you're going to increase your SN2 reaction rate. Your SN1 reaction rate wouldn't be affected at all. Leaving group, all of these reactions, or both of these reactions, are going to depend on a good leaving group. You want a weaker base, and that makes a better leaving group. If the leaving group comes off and makes a strong base, that is a bad leaving group. And we also talked about steric hindrance. Tertiary substrates can only do SN1. Primary can only do SN2. Secondary substrates can do either SN1 or SN2, which basically means we have to look at other factors. And finally, we have solvent. Polar aprotic solvents are going to promote SN2 reactions, and polar protic solvents are going to promote SN1 reactions. So those are all of the factors that we went over, and please make sure that you go over those and understand how they're important to determining which mechanism you have, and then how they're going to affect both of these types of reactions.